Hi, I'm Dan Bauer and welcome back to CBA Office Hours. Today what I'm going to do is extend our linear regression playlist with another episode. Our last episode looked at the inclusion of categorical predictors in regression models, and so we've now seen both how continuous predictors enter the model as well as categorical, and today what we're going to do is talk about interactions. And in particular, we're going to focus on interactions between categorical and continuous predictors today, and then we'll do a follow-up where we look at continuous by continuous predictors in another episode. So just to remind you where we left things off is in our last regression model that we talked about, we included both continuous and categorical predictors, but they simply had additive effects, so there's no interaction present. And so we have some outcome variable, and then we have an intercept, and we have an effect of a continuous variable, x, and then we have an effect of a categorical variable. And we'll say it's just a two-category variable that's been coded through an indicator variable or a dummy variable, and we'll just call that D to indicate it's a dummy variable, so it's just 0, 1. And then of course we have our error term that we add on to that. Right, so that's our simple additive regression model. And if we think about what that model implies, it implies that there's some effect of x holding constant d, and there's some effect of d holding constant x, right? And so we say, well, what's our expected value of y for each of these two groups? Well, we can say, all right, the expected value of y holding x at some constant value, we'll say c, and setting d to 0, our reference group, right? What's that going to be? Well, we've got beta naught plus beta 1 c, and then no beta 2, right? So beta naught plus beta 1 times c. That's going to be our expected value for the reference group. And then for our contrast group, we're going to have, again, we'll set it at that constant value. We're going to have beta naught plus beta 1c plus beta 2, right? And so in that setup, as we talked about last time, our effect of the dummy variable represents the mean difference between the two groups when holding constant any other predictors that might be in the model. And we can see that here is that if we take the difference between these two groups, right, beta naught's going to drop out. We're going to have c beta 1s for each group, and we're left with beta 2. So beta 2 is the difference in the expected values between the two groups, the difference in the averages between the two groups, but with the important caveat that we are holding x constant at c. All right, so this is the traditional setup of analysis of covariance, is that in analysis of covariance we want to look at group differences, but we know there's this additional variable, this continuous variable x that we want to control for, and so we control for that, and then we want to observe what's the grouping effect if we hold that constant. Right, so as an example, some data that I sometimes use when I teach regression is a very clever former student of mine scraped data from Rate My Professor. Right, so Rate My Professor is a website where you can, for professors that you've taken classes from, you can put a quality rating, an easiness rating, and it used to be that you could also provide a chili pepper. They've taken that out. They decided that became controversial. But the chili pepper was just whether you thought your professor was attractive or not. Right? So this enterprising young student of mine, she scraped data from all the professors at the University of North Carolina and got the average easiness rating of all the ratings they had, all the average quality rating, and then whether they had ever received a chili pepper. Right? So we can, although it's kind of a silly data set, we can use this to evaluate a well-known phenomena in social psychology, which is that attractive people tend to be rated as more competent. So we might expect that attractiveness, receiving a chili pepper, is going to be associated with higher quality ratings. But at the same time, teachers grouse all the time that if they teach an easy class, well, they'll get higher ratings, but if they teach a hard class, they'll get lower ratings. So we might be interested in evaluating these effects simultaneously. So D here would represent, well, let's go with Y first. So Y would be the quality rating, right? So how well was this course evaluated by the student? And then X would be our easiness rating. That's also on a continuum. And so we expect some relationship between easiness and quality, but we also have this attractiveness rating, the chili pepper. And so did the professor ever get a chili pepper or not? We might also expect that to affect the quality rating. So here what we're doing is we're saying, well, look, we can hold constant the easiness of the class, right? So pick some number. Easiness is rated between 1 and 5. Pick any number between 1 and 5 and let's hold easiness constant at that number. If we hold it constant, then we can see that there is some mean difference between attractive and unattractive professors and the quality ratings that they receive, and that's represented by beta 2, right? So that's our analysis of covariance of attractiveness. Is there a mean difference associated with attractiveness holding constant that easiness rating? Do we see this kind of classic halo effect, right? So that's one way that we can look at it, but of course we could flip that around and we could say, well, I'm more interested in the easiness effect, right? So we could say, all right, well, I know I have this extraneous variance associated with attractiveness, but what I'm really more interested in the easiness effect, and so I can say, well, what's the expected value of Y given D is equal to some constant? Right now, D is going to be either 0 or 1. We could be talking about attractive. We could be talking about unattractive, right? And I want to know what's going to happen as a function of X, right? Now I'm going to get beta naught plus beta 1 X plus beta 2 C, right? Now that's going to be the same whether I choose my constant, my group, to be 0 or 1. Either way, I get the exact same effect of easiness. So whether I'm looking at attractive professors or looking at unattractive professors, chili pepper or not, I'm going to get the exact same effect of X in each of those two groups, whether I hold D constant at 0, no chili pepper, or I hold D constant at 1, chili pepper, right? So what that's going to translate into is we can imagine, based on this equation, we could plot out what do we expect to observe for Y. And so we've got our X variable, we'll say easiness, and we've got our Y variable, quality. It's kind of hard to write that way. And then we've got quality there. And then we've got two groups, right? We've got D equals 0 or D equal 1, right? So for D equals 0, we're going to have some regression line where we might expect that as a class gets easier, the quality ratings go up. So if D is 0, right, we're going to get this regression line, and this regression line is going to come from beta naught plus beta 1x, and then that gets zeroed out, right? So it's just beta naught plus beta 1x. So we've got beta naught over here where x is 0, and then we've got beta 1 is that effect of easiness. All right, so that's where group is 0. When D is 1, now we're going to add in beta 2, right? And so we're going to get another line, right? And the difference between these two lines is going to be beta 2, and the slope is again going to be beta 1, right? So in this additive model, the effect of X is always beta 1. It doesn't matter which level of the grouping variable D we're looking at, we get the beta 1 effect. And the effect of D is always beta 2, no matter what level of X we look at. It's beta 2 here, it's beta 2 here, it's beta 2 here, it's beta 2 no matter where we go, right? The lines are parallel. This is the parallel regression lines or homogeneity regression assumption that is made in analysis of covariance. All right, so we could fit this model, and if we fit this model with this play data, we get something that looks very much like this. Is there is an easiness effect, easier classes get higher quality ratings, and there is an attractiveness effect. Professors who receive a chili pepper also get higher quality ratings holding constant, the easiness ratings. But what if that's not the whole story? What if attractive professors can get away with teaching harder classes and still get good quality ratings? So maybe that effect of easiness on quality is not really constant. Maybe it's not really just beta 1, beta 1, beta 1, but there's actually a different effect of easiness at each level of attractiveness. All right, so let's consider that. All right, so what we're going to do with our regression model is we're just going to add one additional term. All right, so we're going to add an interaction, beta 3 of d with x. Actually, I'm going to write that a little bit differently. All right, we'll say x times d, right? So it's a product of those two variables, right? And again, we still have the error. So we're literally taking a product of this x variable with the d variable, right, where d is 0, 1, binary indicator variable. And we're adding that as one more predictor to the model. Now notice what that's going to do is if we say, well, what's the expected value of y given x and d, right? So let's say where, let's just say where d is equal to 0 to begin with. All right, so if d is equal to 0, then we're going to get beta naught plus beta 1 x, and then beta 2 is going to drop out because d is 0, and beta 3 is going to drop out because x times d will be 0 whenever d is 0. So we have this regression, or this simple expression here. All right, well, what if d is 1? Now we're going to have beta naught plus beta 1x plus beta 2 plus beta 3x. Now notice what's happened there is we start off with the line for the reference group, but then we add to it these components right here. Now we can rearrange those terms a little bit to better highlight what that's doing. I'm just going to rearrange that to pull out the two terms that don't involve x from the two terms that do. All right, so we now have this expression, and what you can see is that we're adding beta 2 to the intercept of a line, and we're adding beta 3 to the slope of a line. Now, oftentimes what these are referred to as are simple regression lines. And so we have, for the group d equals 0, we have a simple intercept beta naught and a simple slope beta 1. For the group where d equal 1, we have a simple intercept beta naught plus beta 2, right? Beta 2 is the difference in intercepts between the lines. And we have a simple slope of beta 1 and beta 3. Beta 3 is the difference in slopes between the two lines. All right, and we can plot that out to get a better sense of that as well. Erase our error term just to make a little more room. Right, so we plot that out. Now we have our x, right, remember our easiness. And we have our y, our quality. Yeah, that was a little better. And we've got our d is going to be 0 or 1. So maybe for the less attractive professors, we observe this, right? So this is d0, and so we're going to have, wherever x is 0, we're going to have our beta naught. Right, so that's going to be our beta naught right there. And then for a 1 unit change in x, we're going to have our beta 1. Right, so when d is 0, we have a line that is defined exclusively by beta naught and beta 1. Okay, well, what if d is 1? Now we've got to add beta 2 to our intercept. So we start here at beta naught and we add, let's go up a little higher, we add to that our beta 2, right? And that's where our simple intercept is for our contrast group, our chili pepper professors, right? And then we say, all right, well, what's the slope for them? It's going to be beta 1 plus beta 3. So we have this beta 1 slope, but we're going to add to that the beta 3 slope. Now, in this case, I expect the effective easiness to be less lower magnitude for professors who get the chili pepper. So I would expect beta 3 to be negative, so beta 1 is positive, beta 3 is negative, it's taking some of that slope away, and we might get a less steep slope for the chili pepper professors, right? And so this slope right here is going to be our beta 1 plus beta 3. If beta 3 is negative, it's taking away from that slope. All right, so we have a difference in these intercepts of these simple regression lines given by beta 2, and we have a difference in the slopes of the regression lines given by beta 3, right? So oftentimes, especially in psychology, you'll hear this referred to as simple regression lines and an interaction plot. In other areas of statistics, you might hear it referred to as a conditional effects plot. But it's a very nice way to visualize what it is that the interaction is doing in the model. All right, now we have focused on this in terms of looking at how the slopes of the two lines, so the effect of x depends on the group you're in, the value of D, but we could alternatively be focused on how the two groups are different from one another, right? So we've got, let's make a little space here. So we've got our two regression lines for our two groups. Beta 2 is the group difference when x is 0, right? So if x is 0, this drops out, and beta 2 is our group difference. So that's our group difference right here, right? But as x increases, that group difference changes. We don't get the same mean difference between chili pepper professors and non-chili pepper professors at any old value of easiness, right? In the prior model, remember, we could have set easiness to any constant c. It could be 1, it could be 2, it could be 3, right? But here it matters, right? So if we look at a class that is hard, there's a bigger difference. If we look at a class that is easy, there's a smaller difference, right? And that difference is going to be beta 2 plus beta 3x, right? So we start out with beta 2, and then we add to it that interaction term. And again, in this case, we would expect the interaction to be negative, so that initially large difference in quality ratings associated with attractiveness for classes that are hard narrows as we get for classes that are hard, narrows as we get to classes that are easier, right? So bottom line being, attractive professors can teach harder classes without a penalty to their quality ratings, right? Relative to the unattractive professors. Now, I may be, in saying that they pay no penalty, I may be overstating. There is some slope to that line, right? And so that takes us into the next aspect of what we often do when evaluating interactions, is we get our regression coefficients, right? So we're going to get a B0, a B1, a B2, a B3. We could do our significance tests on those. If we get a significant effect of B3, right, then that tells us that the null hypothesis that beta 3 is 0 is rejected, and we believe there to be an interaction, right? So that means the slopes of these lines are different, and the distance between them correspondingly is not constant. Right? So there's a non-constant mean difference between attractive and unattractive professors as a function of easiness. There's a non-constant effect of easiness across levels of attractiveness, right? So if we get a significant B3, we say, hey, we've got an interaction and the effect is not the same. We go to our conditional effects plot. Now what that interaction is testing is, are the two slopes here significantly different from each other? All right, so remember when we first drew this up, fix that. All right, we said that is beta 1 and that is beta 1 plus beta 3x, right? Or sorry, just plus beta 3. We'll say it's just a 1 unit difference that we're looking at here. All right, so we've got that difference in slopes represented by beta 3. If our coefficient associated with that is statistically significant, we say we've got an interaction. All right, now that's a test of whether the slopes of the two lines differ. But what we might also want is a test of the slope of each line on its own relative to a null hypothesis of 0. Right, now it turns out we actually already have one of these. Right, beta 1 is our slope for the reference group, for D equals 0. So we're going to get an estimate B1 for beta 1, we'll get a significance test, we'll get a p-value, and we can see whether or not easiness has a significant effect on quality ratings for the d equals 0, the non-chili pepper group, right, for the reference group. So our coefficient for the continuous predictor is actually going to be our simple slope for the reference group. Now for the contrast group, our simple slope is a linear combination of two coefficients, beta 1 and beta 3. We have the test of beta 3. That tells us this slope is different from this slope, but it doesn't yet tell us, is this slope on its own significantly different from 0? Right? And so that is why we often will do an additional test on this coefficient. Right? So we'll calculate this simple slope. So this simple slope is, when we get our sample estimates, our estimate of that is going to be b1 plus b3, and we can get a standard error for that combination and do a significance test on that as well. So when we do our interaction analysis, we will first test b3. Is there a significant interaction? If there is, we'll make our conditional effects plot, and then we will typically want to evaluate the simple slopes. Right? So we'll say, oh, okay, well, d can be 0. Is it significant? Is the effect of x significant there? And we'll have that as our b1. If d is 1, is it significant there? Right? It's smaller, the slope is smaller, but it still might be statistically significant, and so we can calculate the standard error and get the t-test. And the actual result with the real data is this coefficient is about 0.4, and this coefficient is about 0.15. And even though this is much smaller than that, both are statistically different from 0. Right? So although they don't pay as much, the more attractive professors don't pay as much of a penalty for teaching hard classes, they do still pay some penalty. Right? They do get a benefit associated with easier classes. It's just that they start higher even at the harder classes. Right? So we can get a test of those simple intercepts and those simple slopes. Now that was focusing on what is the effect of x at each level of d, but again, we can also evaluate what is the effect of d at each level of x. Right? So again, we can say, where is this difference between these two lines statistically significant? Right? Is it's narrowing, it starts out big and it narrows as the class becomes easier. At what point is there no significant difference? Now we could say, well, easiness is rated on a scale of 1 to 5, so I'm just going to look at values of 1, 2, 3, 4, and 5 and see at each of those scale points, is there a significant difference between these two lines? All right, and that would be fine, is what we would be looking for there is b2 plus b3, right? So b2 is the group difference we start out with, and then b3, right, that's how much we're going to change it as a function of what level of x we're at. All right, so that's our difference between the two lines, and we could test that at different levels of x. The only thing that's a little unsatisfying about that is why look at just these particular values of x. Right, so we can alternatively, so we could do that. We could calculate simple slopes, simple effects of d at various levels of x, just like we looked at simple effects of x at the two levels of d. But what's a little unsatisfying about that is x is a continuous variable. And so why should we only look at particular levels of x? Well, we won't go into the details now, but there is another procedure that we can apply here, referred to as the Johnson-Neyman technique, or regions of significance. And what the Johnson-Neyman technique does is it identifies the point at which these differences are significant or not. Right? So it gives you a region of significance. And so we might find by applying that technique, for instance, that the region of significance starts out over here at, let's say, 3.2, right? Which would indicate that for any easiness rating of 3.2 or beyond, the p-value for that difference is greater than 0.05, right? Non-significant. And for anything on the other side of that, p is less than 0.05, and it is significant. Right? So that's a nice procedure that you can apply if you're wanting to look at simple effects as a function of a continuous predictor. So just to kind of recap what we've done here is we have a model with both a categorical and a continuous predictor within it. We've included an interaction to allow the effect of one variable to depend on the other. So we don't have a constant effect of x at each level of d. We don't have a constant mean difference by d at each level of x. Instead, we have lines that are converging or spreading apart. And so we don't have parallel regression lines in this interaction model. So we've added that interaction term. When we find a significant interaction, we generate a conditional effects plot. Upon having generated the conditional effects plot, we will typically want to evaluate the significance of the simple regression lines or the simple effects in there. And we can do that in either direction. We can look at the simple effect of x as a function of d, or we can look at the simple effect of d as a function of x. Now, if we have a moderator that is a categorical variable, d, so we're looking at the slopes of x as a function of d, then we just have two levels of d at which to calculate those simple effects. On the other hand, if we're treating x as the moderator and we want to look and see how does that mean difference vary as a function of x, well, now we have to pick what levels of x do we want to evaluate that at. We could pick a few values, or we could apply the Johnson-Neyman technique and identify at exactly what values would we find a significant difference and at what values would we not. Right. Now, I've focused on the case of a single grouping variable with 2 levels, but of course this extends. You could have a grouping variable with 3 or more levels, and then you would just have additional dummy variables and additional interaction terms to account for that. All right, so with a 3-level variable, we'd have 2 dummy variables, we'll call them d1 and d2 to differentiate that, and we would add in 2 interaction terms, x by d1 and x by d2, and then we would have 3 lines and 3 slopes to test instead of just 2. So the procedure is generalized nicely. Now, what we'll talk about in our next episode is how do we generalize this approach to the case of 2 continuous predictors that are interacting with one another. And so that'll be next time. But hopefully this gives you a good sense of how you can do categorical bicontinuous variable interactions in the regression model. And given that a lot of our theories really focus on interactions and what those interaction effects look like, that's something that we do quite a lot in our statistical analyses. All right, well, thank you, and I will see you next time.